Hey everyone, in this video we're going to be talking about path independence, conservative fields, and potential functions. So let's jump right in and define path independence and what it means for a field to be conservative. So here's our definition, and this is just the fine print statement we need to include at the beginning. Let F be a vector field defined on an open region, which we're going to call D, in space. Alright, so the first definition is going to be for path independence. So the line integral, which is the integral over our curve C of f dot dr along a path C. C is just our curve, and this is going to be from one point to another point. So from the point A to the point B in our region D is considered path independent. So path independent in the region D if the value of our integral, so of our integral from A to B, is the same over all paths from A to B. Okay, so hopefully that makes sense why it's considered path independent. So all paths from A to B. And then we'll also define conservative. So, and the field that we're calling capital F is considered or called conservative on the region D. And so conservative fields is like, think of it as like conservation of energy is one way to think of it. So pretty much what this is saying is that we have path independence if when we integrate over our curve from point A to point B, it really doesn't matter what path we take as long as we start at point A and we stop at point B. We're going to get the same value for our integration every time, and that's considered path independence. And when this happens, when this is the case, then the field F is considered conservative when this is true. Okay, so let me just briefly mention some examples, and then we'll keep going. Okay, so some examples are a gravitational field and an electric field. And so a gravitational field would be like one that represents the effects of gravity. And in that case, we would say that F would be m times g, where m is a mass, and the gravitational force on the mass would be F. And for an electric field, we could say, and that one represents like the effects of electric forces. So we could say that F would be Q times E, where F is the electric force on a charged particle where in that field, so that particle would be Q, or that charge. So what's interesting or important here is the work on either one of these objects in these fields. So I'll say the work required to move, we'll say a mass or a charge, depends on where it's coming from and where it's going. So on the initial and final positions, and what it doesn't depend on is the path. So not on the path taken to get there. So that's interesting. It's independent of the path, the work that required to move the object. It just matters where you start and where you stop. Okay, so another thing that we want to mention here is just a few notes about the domain of our region D. So we're going to consider domains. This is D. So consider domains that are connected. Okay. And so what that means, if it's connected, if it there's points joined by a smooth curve, and actually some of the results that you come across require your region, so require D, to be simply connected. And you don't really have to focus too much on this. You just, most of the problems that we'll work on, this is true, but just so you know what this means, simply connected, it kind of is like not having a hole, like a loop in it. I'll just briefly draw a picture, but if you had a region like this, let's say, make that more smooth here. Let's say this was my region, and this is simply connected, but let's say that there was a hole in the center, not in the region. Then what happens is, to be simply connected, if you can make a loop in your region, so this red part is a loop, if when I start to contract that loop, like make it smaller, it has to still be in the region. Notice if I made that contract that loop, it's no longer in the region because that part in the center is like a hole. So simply connected means that we don't have like holes like that. Okay. And then the other thing is that we consider curves that are called piecewise smooth. So curves that are piecewise smooth, and even if it's different pieces that make up the curve, they're smooth when you connect them. Alright, so next what we want to do is we want to go over a very important theorem. Alright, so here is our important theorem. It is the fundamental theorem of line integrals. So I just have like a fine print statements there for us first. I don't have the statement of the theorem yet, but this is an important theorem for line integrals, as you can tell from the word fundamental, just like fundamental theorem of calculus, fundamental theorem of algebra, things like that. So the statements that have to be here, like I call them fine print statements, is that C has to be parameterized in a smooth curve joining points A to B. And then little f is a differentiable function with a continuous gradient vector field. So capital F is the gradient vector field, so it equals the gradient of little f. And that's on a domain D containing our curve C. Alright, so here is what the theorem says. The integral over our curve C of f dot dr is equal to the integral from point A to point B of the gradient of f dotted with dr. And here's the nice part. This is just f evaluated at B minus f evaluated at A. And so this is going to be really nice to allow us to calculate very quickly these line integrals. So this is just where little f is what's called a potential function. So it's the potential function of, or for capital F, our field. Alright, so we will do an example a little later on how to find that potential function. But this is our theorem, our fundamental theorem of line integrals. This is the main statement right here. Okay, let's go ahead and try this example. So the force field F, capital F, which we're already being told that it is the gradient of the function little f, and little f is -1 over x squared plus y squared plus z squared, so that's given. And we want to find the work done by the field f in moving an object along a smooth curve C that joins the points 1, 0, 0 to the point 0, 0, 2, that doesn't pass through the origin. Okay, so what do we know? We know from previously that work is the integral over our curve of f dot dr. And now we know from our fundamental theorem of line integrals that this is the integral from a to b of the gradient of f dot dr, which is f evaluated at b minus f evaluated at a. Okay, Okay, because we're told that capital F is the gradient of f, so we know that this equals this. And so this is really nice because we just have to evaluate f of our final position minus f of the initial position. Okay, and so just plugging those into our function, just plug those right on in up there. We'll just do it really quick. -1 over 0 plus 0 plus 4 minus -1 over 1 plus 0 plus 0. Simplify that and you're going to get 3/4. Yay, and that's it. Okay, so that is our final answer. Okay, well, so just briefly to mention, for this particular problem, in this case F, capital F, the field, it could model a gravitational force, like due to a planet. And then the function little f here could represent the gravitational potential energy. Right, so what I want to show you, and we won't go through it, I just want to mention it, is the long way. So we're done with our answer, but here's the long way. If you wanted to do this without your fundamental theorem of line integrals, this is what you would have to do. You would have to first find the gradient of f, then we would have to find our parameterization for our curve. So we'll say find r of t, where arc length is going to be our parameterization for our curve, and then we would need to find the derivative of r. Then we would have to compute the dot product of the gradient with dr dt. This is a dot here, dot product. And then finally, then we would have to integrate this. And so that's the long way. And so we say, no, we don't have to do that anymore. Yay, we already can just simplify the process using our theorem, fundamental theorem of line integrals. So that's good news. All right, so we'll do some more examples in just a little bit, but let me give you another theorem. And so this next theorem is about conservative fields. So conservative fields are gradient fields, and here's what the theorem says. So if we have a vector field f, and this is going to be equal to mi plus nj plus pk. So m, n, and p are just functions of x, y, z. And so a little bit of fine print, I'll just mention that this field has continuous components. So m, n, and p are continuous on some open connected region. Okay, but this field is conservative if and only if, so if and only if, that means this statement goes both directions, that f, the field, is the gradient of a function f. So f is some differentiable function. So this is the statement of the theorem, that your field is conservative if it's the gradient of a function f, and the opposite is true, the other direction. If your field is the gradient of a function f, then the field is conservative. So that's what if and only if means. You can go both directions with that statement. So let's go ahead and take a look at an example. Alright, so here's the example. Let's find the work done by the conservative field f, which is yzi plus xzj plus xyk, where little f is the function xyz. So find the work done in moving an object along any smooth curve joining these 2 points, -1, 3, 9 to 1, 6, -4. Okay, so what do we know? Because we're told that the field is conservative, we know that capital F, the field, is equal to the gradient of the function little f. Okay, so that's because we're told that this is conservative. And because that's true, then we know that the work is very similar to the last problem, that our integral for work of f dot dr just becomes our integral from a to b of the gradient of f dotted with dr which is just our function evaluated at the ending point minus the function evaluated at the starting point. Okay, so very, very similar to the last one, and in this case our function is x, y, z, evaluated from 1, 6, -4, then minus the function evaluated at the starting point, -1, 3, 9. So just plug those in. It's just the product, x times y times z. And so that's going to be -24 plus 27. Final answer, 3. Okay, so that's nice and easy to compute with our fundamental theorem of line integrals, because we're told that this is conservative and we were given the field and the function f. We will do the ones a little bit trickier where we have to find the potential function in just a little while and also check if a field is conservative. So that's where we're headed. But next, let me give you another useful theorem. Alright, so this theorem is the loop property of conservative fields. And it says the following: if we have an integral over our curve C, and this notation right here, this means that we're integrating around a closed path. So the integral around a closed path and of f dot dr is actually 0. And this is going to be when this is around every loop in the region D. Okay, and so that's every closed curve C is another way to think about that. And this statement is equivalent, and this is going to be a two-directional arrow because the opposite direction will also be true. This to saying that the field F, the field capital F, is conservative. And this is conservative on the region D. Conservative. Alright, so this double-sided arrow means that if the field is conservative, so starting from the second sentence, then this integral on every closed curve or every loop is 0. And in the other direction, the integral is 0, meaning that the field was conservative. So if and only if again, they imply each other. Alright, so let's go ahead and just kind of summarize the two theorems we looked at so far and show what relates. So we know that if f is the gradient of some function little f, that means that f is conservative. That was from our first theorem. And we know the opposite is also true, or the other direction, that if f is conservative, then it's equal to the gradient of a function. But we also know now that if f is conservative from this other theorem, that the integral on that closed path or loop of f dot dr is 0. And we know if that integral is 0, then f is conservative. So we can put all these together. And so this is on any region D or any loop in D. So this is sort of a summary statement for our theorems that we just looked at. Okay, so now you may be wondering if you're thinking about some of these things, and I briefly mentioned that this is where we were headed. Well, how do we know if f is conservative? So far, we've just been told. Okay, we've been told, oh, this function was this field was conservative. So my question then is, how do we know if f is conservative? Because if we know that, then that's very helpful. We can use these facts that we've been working with. And another question is, if f is conservative, so let's say we figured that part out, how do we find a potential function? That's little f. So how do we find a potential function that's little f, and that's because that means that capital F, our field, equals the gradient of little f. Alright, so these are both valid and important questions, and we're going to answer both of them. Alright, so we have first what's called a component test for conservative fields. So the component test, and this is a test, meaning you can use this to find out if a field is conservative, is the following. So if you have your field f, where m is the I component, n is the j component, and p is the k component, and it's on an open, simply connected domain, then your field f is conservative if and only if, so again that means that these statements go both directions, the following are true, and you have to compute some partial derivatives. Okay, so there's three equations here. If you compute the partial derivative of m with respect to y, and that's the same as the partial derivative of n with respect to x. Okay, if that's equal, and then you say partial derivative of n with respect to z is equal to partial derivative of p with respect to y, and last, if the partial derivative of p with respect to x is equal to the partial derivative of m with respect to z, then the field is conservative. So you want to compute all three of these and make sure that they are equal to each other. Alright, something else real quick to mention, but this will come up later, but I do want to just briefly tell you about it. There's a special vector here with these partial derivatives, and so the vector is called the curl of f. Is called the curl of f. And so again, that'll come up later, but I just wanted to briefly mention it now because we were looking at these equations here with these partial derivatives. Alright, so let's go ahead and try an example. So the example says that to show that this field, given here f, is conservative over its domain, and then find a potential function for f. So then find little f, that's the gradient. Alright, so let's start with showing that it's conservative. Alright, so what do we know? We know that m, the component for I, is e to the x cosine y plus yz. We know that n is, for the j component, x times z minus e to the x sine y, and we know that p for the k component is xy plus z. Okay, so we have to check our partial derivative equations. So partial derivative of m with respect to y, let's compute that. Okay, so looking at m with respect to y, so here's y, so e to the x is a constant right here, and so the derivative of cosine y would be negative sine y, and e to the x is some constant, so negative e to the x sine y, and then the derivative of yz would just be 1 times z, so plus z. Then let's check that that equals, so we're going to question, does that equal the partial derivative of n with respect to x? Okay, so looking at that one, with respect to x, this derivative here would be z, which we have here, and then the derivative of e to the x would just be e to the x, where negative sine y would just be a constant, and so that's what we have. So yes, so far so good. We have that as equal. Alright, so now let's keep going and check the other two possibilities. Alright, so next, the partial derivative of n with respect to z. Okay, so looking at n with respect to z, it's only right here, and so the derivative of that would be x times 1, which is just x. Now we ask, does that equal the partial derivative of p with respect to y? And so looking at p with respect to y, this derivative would be 0, that's a constant. So derivative of x times y would be 1x, which is x, so that's correct. 2 out of 3, it's good so far. Let's check the third one. Partial derivative of p with respect to x. So looking at p with respect to just x, that derivative there would be 1 times y, so that's y. And then we want to ask, does that equal the partial derivative of m with respect to z? So looking back over here at m, z is only right here. So derivative of this term would be 0. And derivative with respect to z here would be y times 1. So yes. Alright, so we checked all three, and so we can conclusively say F is a conservative field. And so that part's done. Now, second part, we were asked to find a potential function. I haven't shown you how to do that yet, but let's do it right now. Alright, so to find a potential function, that's little f, and what do we know? We know that capital F, the field, has to be equal to the gradient of little f. So we're going to use that information to find this function. Okay, so how do we find this? All right, so this is our steps. All right, so that would mean that the I component for our field must have been the partial derivative of our potential function with respect to x. This is by definition of the gradient vector. Okay, and very similarly, the n or j component of our field was from the gradient, partial derivative of our function with respect to y. And then same thing for p, partial derivative with respect to z. Okay, that is just from the definition of the gradient function. So these are things we know. We know that those are true. So then how do we find the function? How do we find little f? So to find f, we have to integrate, because we're starting with the derivatives, the partial derivatives. So we integrate, and so we're going to integrate m with respect to x to get back to f and find that function. We're also going to integrate n with respect to y and integrate p with respect to z. Okay, and then once we do that, we're going to compare the results. Okay, because we're going to get possibly three different things, but they all have to equal each other. And so I'll show you what I'm talking about with our example. And so our function that we're looking for, f, is the answer to all of these integrals, because we're integrating the partial derivatives to get back to the function f that we're looking for. But we just basically have to line up our results and match things up. Okay, there's a few different ways to kind of do this if you know you're working with the derivatives, but we're going to go ahead and do it this way, and I'll show you what I mean by this process. Okay, so that's our steps for finding a potential function. All right, so let's do it for this specific example. Okay, so we'll go ahead and call it f1 just to keep track, because we're going to integrate 3 times. So our potential function is the integral of f of m dx. So for us, that's the integral of e to the x cosine y plus yz with respect to x. Alright, so let's go ahead and integrate this. We are going to get, if x is our variable of integration, integral of e to the x is just e to the x, cosine y is a constant there, and then the integral of yz is xyz, because yz is just a constant. And then we need to add in some constant back here. I'll call it c1. Okay, so let me mention what this c1 is, because it's going to come up in our other integration in just a moment. So I'll say where c1 is actually a function or constant function of the other 2 variables that we didn't integrate with respect to, so y and z. All right, so let me rewrite this, because it'll help us in just a moment when we put all 3 of these together. So then, so far, f1, our potential function, is e to the x cosine y plus x, y, z plus some function of y and z. Okay, now we're going to do it again, and we're going to integrate this time. I'll call it f2. We're going to integrate n with respect to y and see what we get. So n was xz minus e to the x sine y, integrating that with respect to y. This is a z. Okay, so let's do that integration. With respect to y, that's going to be x, y, z for the first term, because x and z are constants. And then integral of sine would be negative cosine. E to the x is just a constant in the front, so that's going to be integral of sine, negative cosine, y, plus, I'll call it c2. And c2 is going to depend on the other two variables that we didn't integrate with respect to, so x and z. So I'll say that f2 looks like x, y, z plus e to the x cosine y plus c2, which is a function of x and z. Alright, let's do this one more time, and we'll call that one f3, and this time we're going to integrate p with respect to z, and so p was x, y plus z. Integrating this with respect to z, we're going to get x, y, z for the first term, and then z squared over 2 for the second term, and I'll say plus c3, which depends on the other two variables that we didn't integrate with respect to, so that would be x and y. So that will be what we call f3. Alright, so compare the three. That's what we need to do to find our potential function. So we know that these all should be equal, because these all were supposed to represent our potential function. So we have to just line things up. So f1 was e to the x cosine y plus xyz plus c1, which depended on y and z. Okay, I'm going to line up what's in common. Now if I look at f2 also had an xyz. I'm looking back up here at our work, and it also had an e to the x cosine y. Okay, again I'm looking right here, and then we had plus c2, which depended on x and z. Alright, one more time. So f3 had an xyz, so let me line that up with the other ones. xyz. Then I had this other function that, or this other term that we didn't see just yet, c squared over 2, and then plus, actually let me move this one over here. We're going to move it over to the front, c3 of x and y. Here's why I put these in the order I did. Take a look. This function of x and y, what we had in the first two integrals when we integrated, was a function of x and y. Okay, so that means c3 must be e to the x cosine y. And then take a look in the back here. This last term, z squared over 2, this is a function of z, which we were looking for a function of maybe x and z or y and z. And this one's just a function of z, so we didn't really need the x and y part. And so I'll just kind of clarify this hopefully. Notice that c3, which is a function of at most x and y, is e to the x cosine y. So it doesn't have to be a function of both x and y, but this one just happens to be. And then c1, which was a function of at most y and z, it equals c2, which was at most a function of x and z, and it's z squared over 2. So these two, they were at most a function of two variables, but they're actually just both a function of the one variable z. Okay, so here we have it. Put it all together. So therefore, our potential function, we just found it, f of xyz, is the common term, e to the x cosine y, which was in the first two, and it represents this c3 function in the third one, plus x, y, z, which was in all three, plus z squared over 2, which was in the last integral, but it represents these two other functions from the previous two that we didn't account for from integrating. Let me hopefully make this make sense really quick. Why c1 and c2 equals this z squared over 2 is because when we integrated for the first one, if we go back and take a look really quick, when we integrated the first one here, we were only looking at x as a variable. So when we integrate and go backwards, anything that had a z or a y in it, anything that had a z or a y in it, if we differentiate it, it would be 0, because we were differentiating with respect to x and then integrating backwards with respect to x. Same thing happened on the next one. Anything with an x and a z in it, because we were considering just with respect to y in the second one, if we go backwards and we differentiate it, then if we're differentiating with respect to y, then this term here, because it only had x's and z's in it, would have been 0. This last part that had a z in it, that just takes the place of what would have been there. That's why we want to do it all 3 integrations. You can just sort of look over at the derivatives and match things up as you go, but this is the technique that I use, and it works every time. Okay, so now one last thing, I do have to add a plus regular c to this function, because there could have been a constant there for any of these integrals. All right, and then one thing to note is that there are actually infinitely many potential functions. So when you find a potential function, it's just one of infinitely many, because of the possibility that there was some constant. So infinitely many potential functions of f, and it's because of this c here, one for each different value of c. All right, so that's how we find a potential function. All right, the last thing we're going to talk about is about differential form and exactness. So it's often convenient to express work and circulation integrals in differential form. So that would be this form where we have m dx plus n dy plus p dz. And then that's because then this would equal, that form of the integral would equal our integral from a to b of the gradient of f dot dr, which is just little f of b minus little f of a. All right, so let's define this differential form and also what it means to be exact. Okay, so any expression m of, we'll say x, y, z dx plus n of x, y, z dy plus p of x, y, z dz is in differential form. So that's what that looks like. Okay, so differential form when it looks like that. Then a differential form is exact. So a differential form is exact. So on our domain D, on D, if the following is true: m dx plus n dy plus p dz equals the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy plus the partial derivative of f with respect to z dz, and we call that df. And this is for some scalar function f, little f, throughout the region D. All right, notice that this is just m is a partial derivative with respect to x of our function f, and so on for n and p, like we saw just a little bit ago when finding the potential functions. Now, how you figure out exactness, there is a component test for this, and the nice thing is you already know it. So the component test for exactness is the same as the component test for a conservative field. Okay, so we're going to do one last example. So this example, we're going to show that y dx plus x dy plus 4 dz is exact, and then evaluate the integral over any path from the point 1, 1, 1 to the point 2, 3, negative 1. Okay, so testing first for exactness. We've already done this, so we'll go through it pretty quickly. We were just doing it a little earlier with conservative fields. Okay, so test for exactness. We have the partial derivative of m with respect to y needs to equal the partial derivative of n with respect to x. And let's take a look at both of those real quick. M is right here, and that derivative would be 1. N is here, that derivative would be 1, so those are both equal. Then partial derivative of n with respect to z needs to equal partial derivative of p with respect to y. So those ones, let's erase this. That would be partial derivative here with respect to z, which would be 0, and then partial derivative here with respect to y would also be 0. Alright, one more time. This one, we have partial derivative of p with respect to x needs to equal partial derivative of m with respect to z. P is 4 with respect to x is 0, m with respect to z, that's also 0. So yes, alright, so it is in fact exact. Okay, so that implies that it's exact, and then what that means is that y dx plus x dy plus 4 dz, our differential form is df for some function f, and then that means that our integral that we were asked to find back here equals that function evaluated at our points, at the second point minus the first point when we plug them in. So now we just need to find that function little f. So this is similar to our last problem. Okay, so let's go ahead and do that. So we know that our function f, we'll call it f1, is the integral of y with respect to x from this part right here. So that would just be xy plus, I'll call it c1, a function of the other two variables, possibly y and z. Okay, then f2 would be the integral of x dy, that's from this part here, and so that's just going to be xy plus c2, function of the other two variables, x and z, and then f3 would be the integral of 4 dz, which is from this part right here, and so that's just going to be 4z plus a function of x and y. And so putting those together, f1 equals f2 equals f3, notice that f of x, y, z would have to have the common term of xy plus 4z plus some constant c, because this one is the function with respect to y and z at most, or x and z at most, and then this part here, x and y, is the function of x and y from there. Okay, so now the very last thing to do is to just recognize that our integral that we were asked to find between our points, which was y dx, x dy plus 4 dz, just equals f of our second point, 2, 3, negative 1, minus f of our first point, 1, 1, 1, and we can plug those into f that we just found right there. Okay, so that's just going to be 2 times 3 plus 4 times negative 1 plus c minus 1 times 1 plus 4 times 1 plus c. And so we're going to get, after we simplify, 6 minus 4 plus c minus 1 minus 4 minus c, which simplifies to negative 3. Final answer. There we have it. Okay, so we did it. We learned a lot about our conservative fields and potential functions, and now a little bit about differential forms and exactness and path independence. So that's it for now. Thanks for watching.